Okay, welcome everyone about my talk about microservices. As already announced, I'm Urs Peter, senior in the sense that I'm already along in this industry, then you get by age senior itself. In my daily job I try to be as much possible with my hands in the dirt, so that I still touch real things and not only get lost in concepts. I'm also a frequent speaker on conferences, you might have seen me. Trainer at the CB Academy, and the focus areas I have as a trainer is basically on two areas. So I have this kind of distinction between do the right thing and do the thing right. And I think in engineering both are very important. You cannot have one without the other. So if you're a perfect programmer but you have a messy architecture, you still probably deliver crap. And also the other way around. If you have the perfect architecture but you can't code it correctly, you still end up with crap. So I think both deserve a lot of attention. And from that perspective, also the author of a variety of trainings here. So the event-driven part is definitely on the area of do the right thing. Well, you might know me from Kotlin. I do a lot of stuff with Kotlin. So I'm also a certified Kotlin trainer, talk a lot about Kotlin. But said today, it's not about do the right thing, which would be Kotlin, do the thing right. Well, I won't present this talk totally alone. I will have Jens with me. And he's from Suspicious Inc. You know, he's a bit kind of the guy who, a bit old-fashioned. He was an engineer once, but then grew up to management. So he's asking these stupid, annoying questions, which of course are not always that stupid. So you will see him pop up once in a while. Okay, so a bit more about you. Who of you is dealing with a microservice architecture? Okay, that's quite a few. It's about half, more or less, yeah. Who is particularly happy about his microservice architecture? Wow, that's one person. That's still one, right? Okay, the others, so who is working on a monolith? Okay, not half, but 30%. And who thinks that's a wonderful experience to work on a monolith? Okay, a few hands. But definitely not as many as said work on a monolith. So apparently with both styles there is something, right? I think it helps to kind of recap what kind of architectural styles we had, because every subsequent style was influenced by the prior one. And when you look at history, then, well, in the 60s, more or less, we started out with serious computers. And there you had a monolith. Why did you have monolith at the time? Well, you only could have monoliths because the hardware was monolithic. You had mainframes, huge computer, and everything had to happen on this mainframe. So you didn't have a choice than doing a monolith. And as you can see, we did this for quite a long time. Up till now, it's getting hotter again, monoliths. Then about 2000, maybe the ones also with gray hair in this room remember this epoch, which is service-oriented architectures. So apparently these monolithic approaches had some issues. Otherwise you wouldn't come up with something new, right? So they tried SOA, but apparently SOA also had its issues. And up to 2010, we then had actually the next kind of wave, which were microservices, which apparently also are not definitely are necessarily the holy grail. See more of that. So what's wrong with the monolith? Well, the interesting thing is when you start out with an application, I think you're not talking about a monolith. You're talking about an application, right? Because it's just this application. You're probably also not going to talk about a microservice. It's small, you have overview, everything is fine. And this is the stage when it's this application, everything is actually perfectly fine. It's a good time you have. Because reason is simple. It's probably one repo, few people work on it. It's very consistent because most of the time you just talk to a database. And that's a very easy way of ensuring consistency, atomacy, and so on. And that's probably also one of the reasons why everything's so reliable. There's just a few components in the whole. And the reason for that is because we are facing a minimal amount of distributed programming. Actually, the only distributed part we have is connecting with our database, and that's kind of manageable pretty well. Unfortunately, or fortunately for the business, things start to grow. That's when you have a successful business, at least, that's the way things work. And you have this application, and then you build feature and feature and feature. So this ball starts to roll. And then eventually you get this period where you think, okay, it's still doable, but things start to have certain frictions, certain areas, up to the point when you reach this stage, where all of a sudden, multiple teams work on a monolith. And it's very hard to understand because, well, feature and feature, not every feature was probably refactored in a way that you get a very nice consistent whole, just kind of hacked in. Scalability all of a sudden is a big issue too, because if you want to scale, you probably have to scale the database, which can be very costly. And because you have multiple teams working in it, also maintaining it and extending it is really a big problem, which is also true for deployment. So once you need a release manager to ensure that all the features are aligned to go to production, then you probably have a very clear sign that you crossed the line, which can be very painful. And probably then you reached the spaghetti stage. And for developers, I would say this is the time for you to run, right? Because it's just no fun. Who recognizes this to a certain degree? Okay, quite a few hands go up. Okay, cool. And the interesting thing is also Jens kind of figured that out because he has all these drawbacks. You know, it takes so long for these features to go to production. It's very expensive. Developers are unhappy. It's even a challenge to run anything on your local machine because, well, it needs so much resources. So we will lose market opportunities. And I've seen companies that kind of still embracing this model, are even proud of when they get something to production. The release manager is the most important person in the company because he's the one who manages to kind of align all those different teams to a feature set which they put to production. So what are the teams doing? Well, they definitely don't overpromise because you as a team do not want to be the last one who cannot deliver its feature, so you cannot go live. So these teams are then playing safe, just putting a little bit of functionality to it so that they definitely will get to the release date, which for your company is really a bad thing because you cannot evolve as fast as you possibly could. Well, because you had this huge monster and all the drawbacks associated with it, there was this kind of need to kind of do a first decomposition of the whole thing. And this is actually where the software, the service-oriented architecture area did its entrance. So from this huge thing, they tried to split already certain parts up. These parts could still be significant, but it was kind of first effort to split it up, make it more manageable. Because you split things up, now you get remoting. You have to talk to each other. And in the area of SOA, this was done by the enterprise service bus, the TIPCOs. I've heard of these kind of, okay. And did you hear good things about it? No, no. Definitely, yeah, maybe a bit, but questionable. So this is how you interacted with it. So what this approach gave us is that it was probably a bit better to understand the whole because you had smaller portions that had some boundaries. And within a boundary, you probably could, to a certain degree, understand what was going on. Because you had small parts, deployment might have become simpler too. What definitely was a big issue is this enterprise service bus. That was a bottleneck in many regards. Often from a capacity point of view, because scaling this bus is really a big issue. I know of a bank that had some peak in December, and then they actually need another unit of it, but this is extremely costly, so they tried to find out a way to kind of, well, work around that, because scaling is an issue. If you try to run this on your local machine, good luck. So developing is already a nightmare for the developer experience. It's a nightmare too. And what's also often a big problem is that one team is kind of managing this enterprise service bus. And when you, as a project, want to connect to another service, You create an issue which will end up the bottom of the backlog of the service bus team. Maybe in 2 months they respond to you, hey, it takes another month, right? So this is what's really happening in big companies. So this is a spider in the web, which in the end is a bottleneck. And of course, we do not talk about all these nasty standards we had at that time. And scaling was still difficult because most of the time you still had one database. So all these services, they were kind of interacting with one database. And if you want to scale, you have to scale this database, which is again, costly and dear. Well, then eventually we had microservices, which should have learned from the shortcomings of SOA, kept the good ideas, and re-architected them to use modern infrastructure. And if you do things right, then this might look like that, but more on that later on. Well, I think by saying just microservice, you probably don't have a good idea how could we kind of define what a microservice is. What is it different from a SOA component? It's not that clear yet. What really helps is to look at the design principles you should use to design microservices that really live up to their promise. And to be honest, these design principles are not really necessary only for microservices. These are actually design principles that you should apply to every component you design. And if you then make this into a monolith, as it's called, or a modular system, that's really not an issue anymore. But well, microservice, the term is often used, so let's stick now to microservice. But it's definitely applicable to much more than microservices. Well, these are 6 principles, and we'll see in the presentation, we'll use them quite a few times to kind of check what went wrong with certain designs. The first principle is isolation. Well, what does isolation give us? If you have true isolation, then you can scale things. You have this part that is not dependent on other things, then it's easy to put more of them next to each other. When you have isolation, you automatically have resilience. What is resilience? Well, resilience means that if one part of the system fails, it doesn't affect the rest. Like a bulkhead in a ship, if you get some hole somewhere, one bulkhead will get flooded with water, but the ship keeps on floating. Then you have resilience built in. What you also have with isolation is continuous deployment, because when something is isolated, you can deploy it separately. It's not dependent on other things, which is also true, of course, for independent development. Closely related to isolation is autonomy. So what does autonomy mean? Autonomy means that you have all the information in your component to make independent decisions. Right? An autonomous vehicle can drive by itself. And when you kind of look at it from a technical perspective, this means that a component is able to publish its own API. Important side note, API doesn't mean a REST API or a GraphQL API. It can also be an asynchronous event-driven API. Right? We're tempted to think in APIs like the common ones, but API means just a contract to the outside world which tells you how you're going to talk to the thing in a structured way. This one is, I guess, the most important one, single responsibility. And that was actually one of the key drivers for microservices, because as a company, you want to scale quickly in terms of features, right? And when you keep things simple and bounded in that sense, well, then you achieve functional scaling. If you have this huge monster, you've seen that before, multiple teams working in it, then you have a lot of coordination that needs to be in place to evolve. But when you have really these independent components that do one thing right, well, and you do this many times in company, replicate it, then you could scale quickly. But how do you get to single responsibility? That's actually a topic for a different talk. Event storming or domain-driven design can help you to define the so-called bounded contexts. And this is also a kind of art to get that right. I said it would be a different topic, but to get this right is also a very important part of creating a landscape that has good characteristics. So the most troublesome part of the word microservice, I think, is in the micro part, because it implies something about size, but it really should be about responsibility. So what is your responsibility? However, there is definitely a link to size, because if your size would be a dinosaur, probably you don't have a single responsibility anymore. Probably have more responsibilities. So it might help to do a very quick check on a component you have by asking you these questions. So if you have single responsibility right, you most probably have a component that fits in a head of one person, right? If you have a single responsibility right, then it probably takes you weeks or months to develop it, and not years, right? And what's definitely also important, if you have a single responsibility, then it should be handled by one team and not two. So that's a kind of a good heuristic to quickly scan, are we still talking about one responsibility or many? The next one is also quite interesting, which is exclusive state principle. And exclusive state principle is actually deduced from isolation and autonomy. What does it mean? Well, all the interaction between a component, a microservice, should only go with its API and not directly to its database. So the microservice owns its state. So when you have a microservice landscape where multiple microservices use the same database schema, you violated it. And I'm quite sure that sooner or later you get in trouble. The default messaging paradigm between microservices should be asynchronous message passing. More on that later. It's probably something you don't do. The last one is location transparency, and it's probably not so an issue. So what is location transparency in the first place? When you talk to something else, what you actually want is some sort of virtual identifier instead of a static IP address. Why is that important? Well, if you want to be scalable, then, and you would have these static things, that wouldn't work very well, because scalability implies that at a certain point in time, you might have multiple instances that could be scaled up and down. So you, as a unit who talks to these things, just want to have an address that is routed to a healthy instance, but you don't need to know the instance yourself. So this is what location transparency implies. Nowadays with cloud, load balancers, Kubernetes and so on, this is actually taken care of. So this is often not a concern you have to fill in yourself. When we started with microservices, I saw many projects implementing this by themselves, which is very, very tricky. But I said nowadays this is solved, so it's probably not a big issue. Okay, so here you have Jens again. He has this monolith, which has these problems. So they want to rebuild it to microservices. So he gave his architecture department the order, guys, redesign my monolith so that I get rid of all the problems. And he wants us to have a look at the initial design. Okay, let's do it, right? So you see they kind of nicely decomposed the modules we saw in the monolith into 3 parts. So let's just walk through the flow we see here. So you get a request for an order. Then you fetch some customer information, which is needed, right? Need to know where to send it to. Then I call this inventory service to ship it. Eventually, the inventory service ships it and kind of tells me that the order has been shipped. Sounds very straightforward because this is what you do in a monolith, right? In monolith application is exactly what you do. So it's kind of straightforward to design it like that. So again, a good question of Jens, is there something wrong with this design? And the point is there is quite a few things wrong with this design. So what's that? You might be surprised. Okay, so first let's look at coupling. What happens if one of these services is not available? So let's assume that our get customer, our CRM service is not available. Well, you're not going to process any order anymore. That's a problem. You could mitigate that, right? So you could say, I make the CRM service more highly available. That's costly. I could implement some retries, which is probably complex. I could do some caching, which, well, caching, one of the big issues, also costly and complex. So you can mitigate that to a certain degree, but it will come at a significant cost in complexity or money itself. So what you see is that with these approaches, with design approaches, what you get is tight coupling. So synchronous communication leads to tight coupling. And tight coupling always leads to bad availability and reliability. So if one thing fails, the whole thing blows. Same for reliability. The difference between availability and reliability is reliability means that you can expect the same behavior all the time. That's what reliability means. So if you have a very slow service that answers in 5 seconds, as long as it always answers in 5 seconds, that's reliable. Maybe not great, but it's reliable. And available means, of course, that it's there or not there. Let's look at the control flow. So who is in control of the process? With these synchronized communication patterns, what we often get is a single service, or maybe a few single services that own the whole flow. Right? The order service here is the kind of the guy who decides what needs to be done. How about the state? So who is in control of the state? Well, the state is in control of all the microservices by themselves. So they have their own database, their own state. This is a certain separation. So with synchronous communication, what you end up with, if you don't watch out, is this centralized control flow. And that can be good, but it also can have significant disadvantages. You might get a lot of concentration of complexity on one spot. And then you get this monster service for which, if you want to change something in your whole landscape, always have to go through this particular team, and then you end up again at the lowest point in the backlog, which takes a lot of time to get your feature to the market. Now let's also think, how does your system landscape evolve if you add more units to it? What is the impact of adding new services to the mix? So let's assume we would have an analytics service somewhere, and the analytics service, of course, needs some data of other services. Otherwise, it can't do its job. And there are 2 ways, actually, for the analytics service to get its data. Well, you could kind of push it to it, or you could let the analytics service fetch the data. Well, the point is that when you do that, you will increase coupling. And with coupling, you also will increase complexity over time. So with this approach, synchronous communication, you get the so-called interdependent evolution model. So the more things you add, the more tangled things get over time, which will actually lead to less availability and reliability over time for your whole landscape. And this is not kind of invented thing. I've seen quite a few companies that do that reach this particular state. I do also a bit consultancy with KPN. This is more or less where they started. They had a huge chain of services calling each other. And just to get an order right, with every component you add, which has a certain amount, a certain degree of availability, if you know statistics that the more of these you add, the less likely it gets that a whole order will come through, and they had big issues with that. People typing even stuff over from one system to another to get this order eventually done. So, if we address our microservice architecture like that, then what do we get? Well, when you look at the monolith, we had these kind of drawbacks, right? That were the issues we had. The interesting thing is, with this approach, you still have them. Because now it's still difficult to understand. Scaling is still difficult because you have these dependencies. If you scale the order service, you probably have to scale the CRM service because it needs to also handle almost as much load as the order service, because for every order we get this call to the CRM service. Maintenance extension is also a problem because, well, you're coupled, probably still need to coordinate things with the team, which is also true for deployment. However, in the monolithic part, we also had some advantages, right? So we had this consistency, reliability, a minimal amount of distributed computing, which here is also gone, right? So there is a lot of distributed computing going on, and because of that, it's unreliable, and consistency is all of a sudden not transactional anymore. If you call multiple things, consistency is getting a concern. So from that little spaghetti monster, we now evolved to a legion of spaghetti monsters. And I said this is a bit exaggerated, but this is just to make the point very clear. So who of you recognizes to a certain degree what I've depicted here on the right? Okay, quite a few hands going up. Cool. That's nice. So we're on the same page. What's interesting to see here, or what would be interesting exercise to do here, is to look which kind of design principles we violated with this particular design. So let's assume that the single responsibility we did right. Let's assume that. I mean, this you also definitely can do wrong. But for now, just assume that was done right. Okay, that's probably not the big issue. Location transparency, well, our infrastructure takes care of that. Exclusive state, I think that's right. You know, so every microservice has its own database, and all the access to it was done by its API. So that's kind of a given. So apparently, the issues are more on the left, on isolation. That's true, because there are quite a lot of dependencies between the components, so it's not isolated. Same for autonomy, so the order service requires many others to fulfill its task. And I didn't see any asynchronous message passing so far. And if you try to boil it down to the core thing we violated, is that we introduced tight coupling across components. Now, it's quite interesting to look at tight coupling a little bit in more detail. We are tempted to think tight coupling is a bad thing, but that's not true. Think of it. If you have an application that talks to a database, the application kind of fully evolves together with this database schema. They're tightly coupled. Is it a problem? No, that's what we want. So tight coupling allows us to derive a lot of value. And especially when things evolve together and it's on control of a single team, so no coordination is needed to make that happen, tight coupling is perfectly fine. But between those components that are owned by different teams and people, tight coupling gets seriously in your way. Here we have Jens again, and I agree that he's asking this question. So how can we do better? Well, and this is where we get actually to this statement here, which is said to be from Albert Einstein, but that's probably never the case. It's just what people make up. But nevertheless, I think it's a good quote. So if you use the hammer we used so far to fix the problem we introduced with this hammer, probably not going to fix it with the same hammer. So you need a different angle. And this is where basically events come in. What is an event? Well, it's actually something very simple. An event is a fact that has happened. And this is nicely depicted in the way you should name events. So here you see order placed. So the thing, order, and the change is undergone, placed. This is how you name events. So what do events reflect? They reflect the state of the world when it was emitted. So it's not a state of mind, kind of, I want this to happen. No, it's just what has happened at this particular point in time. You radiate that to the outside world and say they can do with it what they want. So there is actually no intent for an event. It's just a message to the world. This is what it was right now. Go do your thing with it. Events should always be processed asynchronously. And do they expect a reply? What do you think? No, exactly. They do not expect reply. Of course, an event can trigger other actions, events or things that need to happen, but you cannot have an event that expects another reply. Then you're not talking about events. Events come with two capabilities, and it's very important to know those. The first capability, what you see here with the delivery guy, is that he rings your bell. Ding dong! So an event can serve as a notification mechanism. And once they have ringed your doorbell, well, an action takes place. You go to the door and open it. So you can use events for that. there's also another capability. Alongside the parcel that you get delivered, there's probably also an invoice. And in the invoice, we have data. So an event can also serve as a data replicator. So let's see if we could use those two mechanisms to remodel our architecture. And if it's a good idea or not, we will leave for now in the middle, but just let's have a look at it. So what you often have with event-driven approaches is that you need some messaging middleware. Kafka is probably most popular right now, but all the queuing system, RabbitMQ and so on. By the way, I've done very effective event-driven architecture without messaging middleware. Talk about it later. It's kind of a very cool case that really gave us a very incredible advantage for the business we're in. So you don't necessarily need messaging middleware, but it's very common to do so. And it definitely also has advantages to do that. So what we would do instead of calling this event-driven service directly, we simply would emit an event of order placed, which then would be consumed by the inventory service. It would process the order. Once it has shipped the order, it would emit another event, order shipped, which could be consumed by the order service, so we know the latest state of the order. So in this particular case, we would use an event as a notification. We radiate to the world, this is what happened. Another part would react on it, does something it, again tells to the world this has happened, and another party again can do something useful with it. But how, so that's kind of a straightforward approach. When we look at this query relationship between CRM service and order service with the customer, how could you design that in an event-driven way? That's probably a bit more challenging. But this is where our event as a data replicator comes in. What you could do is, instead of having order serving calling the CRM service, you simply can have the CRM service emit events about the state change of a customer, or simply emit the customer record, well, in an API kind of contract form to the bus. The order service could consume those events and create a local view of the data that is relevant for the order service. So probably shipping address, or maybe some preferences about how this client wants to communicate, email, text, and so on. And by doing so, once I get an order, instead of asking the CRM service for customer information, you simply can go to your database, tightly coupled, only one thing, and get information from there. So these are two capabilities of events we could use to redesign our architecture. And again, that's, I think, a good question of Jens. Why should this be better, right? So let's see. Let's just go through all the three check marks we invented before, starting with coupling. So what happens if the CRM service is not there? Well, you still process your orders, right? It now can even be that the CRM service is a very crappy system, cheap, or just even something that is running on-premise, doesn't have to scale. As long as it emits those events, that's fine, right? So what you see is that when you use this event-driven approach, you get loose coupling. And by doing so, you automatically get isolation and autonomy, which will highly increase your availability. As long as this order service is there, we can process orders now. How about control flow? Who is in charge of the control flow when we use an event-driven approach? Well, what you see is that basically all the components in your chain own a portion of the process. And the flow itself is depicted by the flow of events. So this basically is your control flow. It's the events. Not necessarily that it's part of one system. The call, the chain of events depicts control flow. So what you get is this decentralized collaborative control flow. which has an advantage that complexity is not concentrated, it's spread evenly. And availability is really awesome. So if one of the systems is not there, eventually everything will be all right. How about system evolution? Landscape evolution. What happens if you add a new service? If you add this analytics service, that's quite simple. It just starts consuming those events like the others. So you get a so-called independent evolution model. So the more things you add to your landscape will not lead to more coupling and decreased availability. You will have more or less the same amount of coupling, but your availability will still be stable the more stuff you add. So this is basically the gist. If you want to apply this pattern in your environment, then of course it might help to get a bit more formalized way of doing that by means of patterns. And the good news is there are quite a few patterns out there. Time is limited, so I can't show you all of them, but I will show you the 3 most important ones that in my career so far really have made a big difference. I call them the 3 musketeers that, well, might save your microservice architecture. And I said component architectures, fill in microservices with application, whatever. Doesn't matter. It can also be between systems, no matter what size they have. The first pattern we're going to look at is CQRS. So who has heard of CQRS? Cool. So most of you have heard of it. Let's walk through it. And before we look closely at CQRS, I think it's good to once more recap what kind of challenge we actually face with actually every architecture out there once they've reached a certain size. The challenge we have is that we need, at a certain point in our landscape, a piece of data we do not own. I mean, it would be awesome if you had this monstrous database where just everybody can plug in and get its data out, but that just has so many drawbacks that this is not happening. So data is decentralized by definition. And the bad news or the inconvenient truth is that data dependencies are always hard, if you like it or not. To process the order, we need this shipping address. And we don't own the shipping address, it's someone else who owns it, but we still need it. So data dependencies, if you like it or not, are hard, are there. You have to deal with it. The way traditionally we tend to deal with it is once we need it, we fetch it. That's the kind of paradigm we thought is normal. And that's kind of logical when you rewrite your monolith, because this is what you did in a monolith. You just did a query in your database, then you got your customer data, then you processed the order. So you just fetched it at the point when you needed it, which is fine within a monolith, but in these microservice architectures, because you get these dependencies, that's what we've seen until now is not a good idea. There are many drawbacks. So what we can do is something which we as developers already do for a very long time in a different context. Probably have heard of dependency injection, right? It's the most common thing. My gray hair, for me, about 15 years ago, that was really a new thing, dependency injection. So once I needed this repository, instead of looking it up in a registry, it was already there. It was injected. I just could use it. And the same principle you actually can do with data too. So instead of fetching data when you need it, you just ensure that you bring it to the place where it's needed. So when you need it, it's already there. Same principle. And this is actually where the CQRS pattern comes in. That's a formalized way of approaching this. So what do you get without CQRS? Well, then you get what probably we are very familiar with, is that we have this domain model, and this domain model has to satisfy two important sections. The first one is you need to change your data, create an order, update it, and so on. And at the same time, facilitate the reads. You want to have a list of orders. You want to have a list of not completed orders. You want to have a list of. So the domain model we've created here kind of has to satisfy both these aspects. Have you had a project where you had to create extremely complex SQL queries to get the data out you wanted? I think most of you not. And that's actually a clear sign that the write model is not very suitable for the read parts. That's why you had to jump through so many hoops to kind of facilitate the read needs of your system. And this is where CQRS can really give you a tremendous advantage. How does it work? Well, what you do is you still have, of course, your write model, order creation, order updating, and so on. But then you have a separate model, which is a read model, which might really look quite different, might even be a different database, facilitating the need for your reads. Maybe normalize it, denormalize, whatever, to facilitate your reads. It's important to well, as I said, you would have commands that would update the write model, and queries would go via the read model. It's important to realize that the read model, of course, is still distilled from the write model, right? The read model is not all of a sudden something that stands by its own. It's really kind of dependent on the write model. Which probably brings to the next question, though, how do I kind of update my read model? How does this work? Well, this is where events come in. So when you update your write model, you create an event alongside with it, and this event would be consumed by the read model, which then would, well, create the read model you need to satisfy your needs. Probably have heard of materialized views in databases. That's probably a very kind of simple way of handling this, which is not as feature-rich as a pure CQRS pattern, but it's kind of close to this idea. When you look in literature how CQRS is often presented, then you see this. You often see CQRS being used in a single application, right? You have a single application that has a write model, maybe with a specific data store for the write model, often maybe relational. And then you might have a separate read model that also would be used in different databases, a database that is good for searching, Elasticsearch for instance. That's the kind of distinction you often see in literature. And you would have to use then events to kind of ensure that these two models stay, at least the read model stays in sync. What's very important to realize is when you do CQRS, you most probably have to deal with this, which is eventual consistency. So eventual consistency means that once I've updated my read model, once for my write model, my read model is not updated simultaneously. So there is a lag in between. You might be tempted to think, that's an issue. The interesting thing is that eventual consistency is the most normal thing in the universe. The only place in the universe where you have real consistency is with quantum entanglement. If you have two of these quarks, I guess, they are really entangled. So if I turn here, then it will turn there. Even now when I talk to you, it's eventually consistent. Voice generated here, goes over the air, gets in your ear, it's processed. You feel like it's consistent, but it's not. So everything when you have a transfer involved, even with light, it's not strongly consistent. It's eventually consistent. Another example, if you order something on the internet, up till now, I've never had it that once I press the order button, someone ringed at my door. Delivered. No, of course not. I mean, it takes days to deliver it. It's eventually consistent. So if you PO think this is a big issue, it really helps to dig deeper and say, okay, where is this a real problem? Because especially prior to IT system, it was the most normal thing that things were eventually consistent. It went from one department to another and so on up to the point when it was delivered. So I said, it helps to discuss it with the PO because most of the time it's not an issue. Okay, where CQRS, in my experience, really shines is not in a single application. Where also had many benefits, by the way, but it shines when you use it across applications. Which means that, and I have all these systems that emit those events, and I have another system like my Elasticsearch that consumes all these events. And by doing so, we can now create an aggregated view of data that is really decentralized. And this might even lead you to new business capabilities because you now can combine data in very interesting ways. I've had this a few times, and once you've done that, it's kind of a wow, revelation. So without kind of combining systems, you can actually create something next to it that integrates a variety of data. In my professional life up to now, I've seen quite a bit of resistance of this notion of replicating data, which is not really justified. Because if you fetch data when you need it, or if it's already there when you need it, the data itself is there at the point when you do your thing, right? When you process this particular request. So data is there anyway. It's just that you put it there at forehand instead of fetching it right away. So from that point of view, it's not justified to say data replication is a point. So it might help if you encounter those differences also for yourself. If you have this feeling, is this a good thing? Just beside your bed table, write it down as a mantra, repeat it, and eventually, I promise you that once you embrace it, you will have a smiling face. Probably many of them, also your boss included. But of course, we have Jens, he's still a bit skeptical, and well, I think he has a point, right? Because when you replicate data, what you really do not want is that the data in the source deviates from the data in the replica, right? So you have to ensure that things are truly eventually consistent. If these two data sources start deviating, well, then we have a problem. And this is actually where our next pattern comes in, which is transaction 2.0. We as an engineer have to ensure, if you apply this pattern, that we can guarantee consistency no matter what of the data from the source to the replica. So what I often see in practice is the following. And actually curious also if you have done this yourself. You get some request, you update your domain model using a database transaction. Alongside with it, you create an event. And then once you've committed your transaction in database, you put the event on the message bus. Who has done this? Most of us, right? Well, sorry to say, this is an anti-pattern. What happens if I've committed my data to a database, but the message bus, for whatever reason, is not there? Well, then the event you create alongside with it, it's gone. Or maybe you just committed the transaction database and this order service component is killed, getting killed. Also no event will arrive at the message bus. So you create inconsistency. The chance is probably very small, but I assure you, when you have enough volume, eventually it will happen. And once it happens, you're in trouble. Alongside maybe with you as an advocate saying this event-driven stuff is great. Like, yeah, you see, it's exactly what I told you will happen. Things are not consistent anymore. So it's really kind of valuable to realize that we need to come up with a very solid solution for this particular problem. And the good news is the solution isn't that hard. Before we look at the real solution, you might, also for the gray-haired among us, to think of this hammer for solving this problem, which is a distributed transaction, so a two-phase commit. Who has heard of distributed transactions? Yeah, I heard of it. Who has used it? You haven't used it? Very good. This has saved you a lot of sleepless nights or headache and so on. I've used it. Well, what is a two-phase commit? It's, in that sense, it looks like a good idea, because what it does is that it does a transaction on two resources, which ensures that either both resources will have its message committed, or its update, or rolled back. Kind of one or nothing for two things. Sounds like a good idea. unfortunately, in practice, it's not the case. First of all, many modern NoSQL approaches, or even Kafka, do not support it. Well, happy you, because then you don't go then you're not tempted to walk on the wrong path. But if your messaging middleware would support it, often it's messaging middleware and a database, like GMS, for if you use the Java stuff, then it's GMS and a database, and many of these solutions allow you to use these two-phase commits. What you get is that your throughput is quite tremendously impacted, because a lot of communication needs to go on to commit to these both resources, which will really hurt the throughput of your system. So if you have large volumes, that doesn't work well. If something crashes, then I've seen really the wildest thing happening. Having a lot of messages in, for instance, dead letter queues, and then you have to figure out what happened, and in the end you still have to look at data and see maybe that some inconsistency has occurred. And what's also kind of not unimportant to realize is it's also a means to decrease your availability, because now 2 resources must be up for you to process your thing. The chance is already high that they're up, but maybe if you do some database maintenance or some message bus maintenance, then you get again in a situation where your system cannot process its request, because it depends on these both resources to be there, so your messaging system or your database. Well, what is the solution then? Quite simple, so-called outbox pattern. Who has heard of the outbox pattern? Okay, a few of you. It's really a very simple pattern. So, what you do is, in your relational model, you would simply create a table, which you call outbox table. Right? Then, instead of only updating your domain model, you would also right away insert the event you create alongside your domain model update in the same transaction, right? So that the event and the domain model update would be committed in the same transaction. That's the outbox pattern. The outbox pattern itself is not that valuable yet, because, well, we haven't yet emitted an event to our message bus so others can consume it. And this is where the polling publisher pattern comes in. So besides the outbox table, you would have this polling publisher, which simply would poll this outbox table, get the events out, and put them on the messaging middleware. Wait a minute, you might say. Ho, ho. Here we also have the possibility that I might have put a message on the event bus, and then when I try to remove the event in outbox table or flag it, no matter how you do it, this transaction still could fail. That's true, but that's not such a big problem. When you design your systems in a way that you ensure that at least once delivery messaging guarantees are in place, everything is fine. At least once delivery semantics implies that whenever you consume an event, you need to have a means somehow to ensure that you know whether you have had it or not. And if you had it twice, then either you just override it with what you had and this doesn't affect anything, or just skip it. And it's good practice in larger systems to use this particular messaging delivery guarantee. So not exactly once, but at least once. Right? You can get it more times. So this is actually where my own solution comes in, which so far hasn't been broadly adopted in the world, but for us was game-changing and works like a charm. We use this in environment in telecom industry. For instance, all the mobile phone numbers you have is managed by a foundation in the Netherlands. This is where I work. When you call on a network of KPN to a number that is on Vodafone, then KPN needs to know that it needs to reroute the request to Vodafone. So it is of uppermost importance that these numbers are synchronized to all the providers in the Netherlands. This is what our foundation does. So whenever you switch from KPN to Vodafone, well, this must be known to both companies for 100%, because otherwise you get rewriting issues, and that's totally not acceptable. And we used exactly this pattern in this context, where we had to guarantee really 100% consistency, which perfectly works. So how does this pattern look like? It's actually quite simple. I was asking myself, if you have this outbox table, then normally you would have this polling publisher to read those events and put it on a messaging middleware. We have a very small team at the client where I am, and kind of keeping Kafka up and running, even if it's managed, I thought, it's just another layer of complexity. Actually, I don't want to have this Kafka. I want to maybe just see if I can do without. So the very simple thing we did is create a server-sent event interface. That's something, have you heard of server-sent events? It's basically an HTTP standard, which allows you to do a GET request, just a normal GET request. And from there on, the connection would stay open, and then the server could send data to you. It's really a way of push data by HTTP. So it perfectly works with your existing API gateway. You don't need to bring up something different to make that work. So you can really push data with HTTP. That's possible. So I thought, okay, if you simply would directly stream the events from this outbox table, well, you're there. And you even have quite a few advantages with that approach. So first of all, you can use standard HTTP. With Kafka, of course, it's different. You have a client, different way of doing things. You can easily expose this stream to the outside world. Exposing Kafka is difficult to the outside world. Here, it's just another endpoint you create, and, well, others can consume it. So in our particular case, we had first VPNs with different companies. We had IBM MQ that was designed at the time, or SOAP services that went two ways to communicate with one another, with VPNs, with security in place. Took us about 2 months to ensure a company can consume our events. Now with server-sent events, they simply have a client connecting to us, and literally in 10 minutes, they are up and running with us. It was really a game changer, because we also could expose our events to the outside world. What's really nice about this is because this outbox table is just an SQL table. So the streamer can now also use an SQL query with a filter. So I could do a select clause, say, okay, you just want to have events of that type. Or you want to reread those events, depending on how long you want to keep it. So it gives a lot of flexibility to tailor it to different needs, which, for instance, with messaging, middleware is not possible. Normally you have to consume them all or nothing, right? That's the limitation you get. And the nice thing is you only have this inbound traffic, so you're still very loosely coupled. So if our system goes down for a minute because of maintenance, the client just tries to reconnect. Once it reconnects, it gets the events it has missed so far, and it works. Implementing this part here is a bit tricky, because you need reactive programming, extensive testing, also with a lot of connections. There are some nifty things in there, but this is something you do once. Make sure this component works very well, and then you just can use it everywhere. And so far, we really didn't have any issues for years now. This approach perfectly works. Maybe you should open source it, but well, didn't have time so far. The only thing you cannot do with solution yet, and I think that's also not something you should do, is to have multiple consumers consuming the data. Yes?
Yeah, this was also mentioned by Greg Young in his earliest presentation.
Okay, cool. I was not aware of that. Nice. So it's an old idea, which I reinvented. Exactly. How hard can it be? Yeah. And it's not that hard. No. Yeah. The only thing you can do, which you, for instance, can do with Kafka, is have multiple consumers that even kind of assure that the load is distributed among those consumers. So multiple consumers consume events. This balancing you wouldn't have in this particular approach. And if you need that, I think then you definitely should use messaging middleware. It's just one stream that gets the flow of data. And for us, we can even process millions within 10 minutes, for instance. So also if you only have one stream, you still can make it work very easily. So for us, it wasn't an issue, but if this is your primary concern, because you have probably IoT data, billions of it, maybe then you have to consider a different solution. So this is for inspiration. The last one is about coordination. So by now we have a consistent way of ensuring our data is replicated. We can replicate it to satisfy different needs, to aggregate data in different parts. What we're probably still lacking is the following. Imagine if we had this order placed event, which then gets consumed by event service, and the event service realized that, wait a minute, I don't have inventory for this order. Which happens, right? Might happen. What do you do then? According to Jens, the following needs to happen. He wants the client to receive a refund, and he wants to inform the user that the goods cannot be delivered. That's what he wants. Well, who takes care of that? That if something goes wrong, these particular actions are executed. This is where the Saga pattern comes in. Who has heard of Saga? Also quite a few of you. Yeah, nice. So what does a Saga do? The Saga ensures the consistency of the business process. So not of individual transactions, but of the business process. Which means that if something goes wrong, the Saga knows how to initiate a compensating action so that everything's getting consistent again in case of an alternative flow that kicks in. So in that sense, a Saga is this coordinated series of local transactions. We've seen we don't have distributed transactions. It's just impossible in our infrastructure. We only have local transactions in one system. So the atomicity with Sagas is with local transactions. This is where we have guaranteed that everything is atomic, but not across services. So how can we ensure that even across services we get consistent? Well, this is the good or bad news. This is you writing code for it. So there's no magic transaction manager that you can say, okay, roll back the thing. No, you have to write code that will call this service, roll it back, ensure that it's re-rolled back, then call the next, and so on. And maybe if everything fails, have some manual intervention. But the Saga would kind of facilitate that. Maybe if everything fails, send a mail to some service desk that will ensure that. Sagas come in two flavors. The first one we actually already seen. This is the so-called choreographed Saga, which simply uses the same means like we've seen before with events, just emit other events that would depict the alternative flow. So if we cannot ship the goods, we simply could say order failed, and then, well, the payment service would pick that up, do the refund, and so on. So we would use events as a means to also facilitate all those compensating actions. It's good to see the advantages, disadvantages of this approach, and also the second I will show to round up. So the advantage, of course, is that we are still super loosely coupled. So if one system is down, just everything keeps on working. That's a beautiful thing. There are also some disadvantages, however. So first, if your flow gets more complex and you have different pieces of logic everywhere, well, reasoning might become a bit difficult over time. Right? So that's something you have to be very well aware of. What's also an issue is that if you all of a sudden have to do a refund, well, there must be some payment information somewhere. So you could either have the payment service keep this information or put it in the event, but then the order service also needs to preserve payment information. So you will have to deal with the data that needs to be shifted around for those compensating actions. To track the current state of your order is also difficult. So what is the current state? Well, you could have a third instance that consumes all those events to kind of create a picture of what happened to it, but that feels a bit awkward, right? So normally this approach is good when you have really greenfield development, new landscape, for use cases where you don't have too many participants, a few instances. The next one would be the orchestrated Saga, and then I will round up. I think time is up slowly. So that's the counterpart of a choreographed Saga. What we have here is a so-called Saga coordinator, that ensures the consistent flow of the whole business process by means of a so-called saga log. So it's a persistent way of knowing what happened in time. And this coordinator also knows what to do when something goes wrong. So if it receives a certain event or a message from a system, then it knows how to initiate the counteraction. You still can use events, so you don't have to all of a sudden tightly couple things with synchronous communication. You still can use the event-driven approach, but you have a more centralized way of handling those actions. Also here, the advantage is probably that reasoning is simple because it's on one spot. So if you go through the code, you see how this business process will function. Instead of going through multiple systems, we'll look at the flow of events. So if you have to change something in your flow, it's on this particular place. The other services are more kind of components that execute a certain task. So they don't own that much logic, which can also be disadvantage, so that too much logic is concentrated the place where this saga is located. So this works well if you have a non-microservice landscape, existing landscape, maybe there's some legacy systems that maybe use events or not, and you have more participants. This is where I would use the orchestrated saga. So, to summarize, yes?
Where do you put those sagas? The last one was clearly in the other servers.
Yeah.
And the first one?
The first one, it's the flow of events, right? It's just all the systems participating in it. So you get it kind of automatically simply by modeling events. So that it doesn't live runtime in a component. Just the interaction of the events you design is the saga. Yeah.
The saga orchestrator has its own database.
The saga orchestrator must be persistent, yeah, because if you get an event back and something fails and you have to restart the thing, it knows where it stayed. So it's only memory that wouldn't work. Yeah. Okay, so as said, if your microservice architecture is in trouble, and I see quite a few hands go up in the beginning of this talk, then I strongly encourage you to look at events. Embrace them. Call in the 3 musketeers. If you started with these patterns, or just look how you could use them to increase one of the shortcomings, then I can promise you that you will be able to tick the boxes of the principles we define. And ticking boxes of principle is never a goal by itself, but I will ensure you, if you can tick those boxes, then you get this landscape where everything will run smoothly, so it gets you a good night's sleep, and for your business opportunity to grow and thrive. That's my experience, and in that sense, this was my talk. Thank you.